All right, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I was off for a week or so, going to various kinds of events, but I am back. So let's see. First question we have here from Nuno has to do with dark matter and asking, is it possible that individual particles have a halo of dark matter like galaxies do? Well, let's talk a little bit about what dark matter is. So when we look in the night sky, for example, we see lots of stars, from which we see light. And the stars have all kinds of nuclear reactions going on that are producing energy, producing light. We get to see the light. But the question is, how much matter, how much stuff is there out in the universe altogether? And we can get some idea of that by looking at the effect on the orbits of other things of what the orbits of things look like. So, for example, if we see that something is kind of circling around some area, then we know that there has to be mass in that area to keep the thing moving in its orbit. And the mass is what's needed to generate the gravity that will keep the thing going around its orbit. If there wasn't a mass there, the thing would just keep going, and if there wasn't any gravity, the thing would just keep going in a straight line rather than being curled up in an orbit. So you can kind of measure the mass that's present in a particular region by looking at kind of the gravitational effect of that mass. And a thing that's been known for about 100 years now is that if you look at galaxies like ours, that where there are stars kind of orbiting around the center of the galaxy, our galaxy is rotating, I think it's every 150 million years maybe for our galaxy, that it does a rotation on its axis. And and that means that the stars are all sort of orbiting around the center. Now, the question is, from the way those orbits work, one can work out how much mass there is altogether in the galaxy. It turns out the mass in the galaxy is like 10 times the mass that we can account for by looking at the stars we see in the galaxy. So there's been kind of a big mystery of what is usually referred to as dark matter, the matter that we can't see as stars, that's not producing energy or not producing light. What is that dark matter that has a gravitational effect but doesn't have an effect on that doesn't show up as actual stars that produce light and so on? And there are some more extreme cases of this where, for example, two galaxies have collided and there seems to be sort of a lump of stuff in the middle that we can't see, that is not luminous matter that still has a gravitational effect. So it seems like there's something that's making gravity but not making stars and light and so on. So there's been a long time question, what is it? Is it, for example, stars that, for example, all kinds of, planets that escaped from solar systems, stars that weren't quite big enough? I mean, basically, if you have a bunch of matter and it's sufficiently big, then the kind of gravitational effect of that matter on itself will pull it in at such so hard that eventually the nuclei of atoms in it will get pushed close together and eventually they'll fuse, and that produces energy, and that produces nuclear fusion energy in the same way that that happens in the sun. And as soon as you get something which is, I don't know what it is, maybe a tenth the size of the sun, maybe a little bit smaller than that, not sure, some definite size, somewhat smaller than the sun, it's inevitable that there'll be enough pressure produced by sort of the gravity of the thing on itself to force nuclear fusion to occur and to turn it into a star. So at least if it's made of ordinary matter, that's what will happen. So there are lots of theories about what dark matter might be, from traditional things that just don't show up as stars to things like maybe they're little black holes. Well, you can kind of see these things where the mass is concentrated in big lumps. You kind of expect to see kind of the effect of that big lump of matter, that big lump of mass going in front of other things. You don't see such effects, or you don't appear to. So that means people tend to think that dark matter is something more diffuse, more spread out, and so on. And so people, and that there's also one of the things that is seems to be the case about dark matter is that if it is made of particles, for example, that the particles don't have a high temperature. They're not, those particles are not bouncing around and hitting each other because they don't, the expectation is that they don't really react with other kinds of matter. If they did, we would see effects other than gravitational effects from whatever this is. And there's sort of a question of does the dark matter interact with itself, but not with ordinary matter? That's another possibility. My own suspicion about these things is that the idea that dark matter is made of particles is just not right. The analogy that I am fond of giving is that in the 1800s, when people wondered, what is heat? Heat is this thing that can affect an object, and heat can flow from one object to another. And people kind of said, well, if it is flowing from one thing to another, the only thing it could be is a fluid, like a water-like thing, that would be some kind of fluid that kind of just goes inside an object and makes it hot and can flow to other objects to make them hot too. And that was what was called caloric or caloric fluid. And that was what people believed heat was until basically the beginning of the 20th century. And it became clear in the end that what heat is microscopic motions of molecules. Now, you had to know that molecules existed, which people didn't know with any degree of certainty until the beginning of the 20th century. But the fact that heat isn't kind of a fluid that flows from one material to another, heat really is a feature of the microscopic structure of materials. So it is my suspicion that dark matter is a feature of the microscopic structure of space. But that's a view that requires that you imagine that space is discrete, which is what we think is true. And it requires that there is some feature of space that is associated with this kind of different thing that produces gravitational effect, but doesn't produce sort of a particle-like effect. Now, so what might that be? How does that work? Well, the prompt here, the question here, had to do with whether there's dark matter associated with particles. So particles like electrons, quarks, photons, and so on, these are all what are usually considered elementary particles. They're usually considered particles that don't have an inner substructure. An electron, for example, so far as we know, is infinitely small. It has, when there is an electron, it has the effect of changing the electromagnetic field around it. It can produce virtual particle, antiparticle pairs. It has a whole coat of sort of quantum activity around the electron, but the electron itself seems to have zero size. Well, that's been the traditional theory for the last 100 years or so. In our model of physics, that really isn't correct. An electron is made, like everything else, as a feature of the structure of space, effectively. It's made from this graph, this hypergraph, that connects the individual elements, the individual atoms of space. So what is an electron? Well, our guess is that an electron is some kind of topological feature of all these connections in the structure of space. So the analog that I tend to use for this is in a fluid which has a bunch of molecules bouncing around underneath. There are features like vortices, eddies in the fluid that involve lots of molecules, and they involve kind of this thing where they're all sort of going around someplace, and you can't kind of, they can't just sort of all, the things going one way on one side, the other way on the other side, they can't just sort of cancel each other out. There's that sort of topological defect in the middle that prevents them from just kind of decaying away by canceling each other out. And so our guess is that particles are features of the structure of space that are sort of tangles in this network, that are tangles you can't easily get rid of. And So what might those tangles be like? Actually, one serious possibility is that those tangles are very much like black holes. Black holes are places where the structure of space, or more specifically, the structure of the graph of causal relations in space and time, it has certain features. And I think the way that and in particular, it has an event horizon, which is a place where kind of effects can go from the outside in, but not from the inside out. It's like a black hole. We living outside the black hole only get to kind of know what's happening outside the black hole. And for us, the black hole just looks like this one sort of integrated thing that doesn't have any substructure. And so that's a little bit like these particles. It's kind of like the electron from the outside. Well, all electrons look the same. They seem to have some definite sort of external structure. What they might be like inside, whether they're even all the same inside, is unclear. But there's maybe an analogy between black holes and things like electrons. So a question then would be, okay, actually a good question is whether there is dark matter sort of collected around a black hole. The dark matter has a gravitational effect. Does it get pulled in to the gravitational to the gravity of ordinary matter? The answer presumably is yes. What the effect of that is around a black hole, I don't know. It's a good question. I mean, I think we're actually getting quite close in our physics project to being able to simulate gravitational phenomena in enough detail that we should see things that are potentially related to dark matter. So that will be an interesting thing. In fact, just last week, we got some nice sort of videos, simulations of two tiny black holes in our models merging. And what's most notable in these videos is that the structure of space is really wiggling around a lot. But yet there's this kind of region that is associated with a black hole that's pretty stable, even though space is kind of wobbling around all over the place. And these are very, very tiny black holes. So these are black holes that might be, a trillionth roughly of a meter across. So the very tiny black holes, but even a very tiny black hole is thought to have many of the same properties as whatever big black hole you might find that came from a collapsed star. So at least we seem to have a hope of reproducing kind of the structure of space-time, the structure of matter, particularly matter that corresponds to black holes, sort of accurately enough that we might see the effects of dark matter. And that's sort of an interesting thing that could arise in our physics project sort of any day now. I think the question of what happens with, quotes, ordinary particles, not black holes, we still don't really know what ordinary particles are like, although they may be closer to black holes than we think. So there's a bunch that is not known there, and that's something I'm hoping to be able to answer fairly soon. Let's see. Oh boy, all sorts of questions here. Okay, Brady asked, how is antimatter made in the lab and what makes it so difficult to produce? Okay, so first point is, what is antimatter? So a proton, for example, is a particle that has a positive charge of +1 unit of charge. The electron has a charge of -1 unit of charge. So that means when you combine a proton, an electron, and an atom, proton is +1, electron is -1, the atom will be neutral if it has, let's say, a single proton, single electron, like the most common form of hydrogen. Okay, but it is something that was discovered in the 1930s, that to every particle, like a proton or an electron, there is an antiparticle. And the antiparticle is basically exactly the same as the particle, except that its charge is the opposite. All its charges, actually, there's other kinds of charge than electric charge, are the opposite of what they are for the particle. So there is an antiproton, which has the same mass as a proton, the same other characteristics, its spin, its whatever, but it has minus the charge of the proton. Similarly, for an electron, there is an antiparticle of the electron called the positron that has a charge of +1 unit instead of the -1 unit for the electron. But otherwise, so far as we can tell, the positron and the electron are identical. They have the same mass, same spin. They're identical in every way except for these opposite charges. Now, one of the things that's a big surprise in a sense is you might think, oh, the universe must be symmetrical between matter and antimatter. How could one have won out over the other? And in fact, when I was younger, when I was a kid, maybe, well, now half a century ago, I suppose almost, it really wasn't clear. The obvious assumption was that the universe would be sort of equal amounts of matter and antimatter. And maybe that there would be, in fact, some of my earliest personal research projects involved trying to figure out whether the universe could separate into regions of matter and regions of antimatter. But it turns out that doesn't seem to be what's happening. It seems instead that the universe is a tiny excess of matter over antimatter. So in the very early universe, there were about, out of every 100 million protons and antiprotons, for example, there was one extra proton. And so the end result is the protons and antiprotons annihilate each other, and you get left over with this residue of protons, and as opposed to antiprotons. So the whole universe seems to be made basically matter rather than antimatter. And how that happens is still somewhat unclear, because the most common theories, I in fact worked on these things back in the beginning of the 1980s, around 1979, 1980, trying to figure out how this works. It's a very interesting exercise in physics. It relies on at least one kind of effect that we haven't really for sure seen in the lab. We think it happens that way. It has to do with the fact that particles can decay in a way that they violate certain symmetries to the point where there can end up being more particles than antiparticles made in the decay of those particular particles. So whether that really happens that way, we, as I say, don't have lab observation. We know some particles have the feature that they decay differently into particles than antiparticles. We don't know whether the particles you would need to account for the excess of matter over antimatter in the universe exist. They're much more. They're particles that are like more than 1 trillion times heavier than a proton. We haven't observed such things yet, but that's sort of the hypothesis about how that works. But so there isn't much kind of, it's not like the universe, not like we just have to go to the next door galaxy, not that that's easy to do, but that we discover the next door galaxy is made of antimatter. It's not. So how do we make antimatter? Well, what happens is that particles can be produced in pairs. So when you can make a proton-antiproton pair, essentially you can make that out of sort of pure energy. What is pure energy? Well, you can have a couple of photons, for example. You can have these photons interact with each other, and these two photons can produce, for example, an electron-positron pair. You can also have, there are all kinds of ways to produce electron-positron pairs. They're quite often produced when you have a particle that's going fast through a material. Then as it interacts with the nuclei of atoms, there you can get pair production. You can get the production of essentially sort of photons, or photons that are associated with the forces that hold electrons into atoms, electromagnetic forces. It's a little bit more complicated here. It involves these things called virtual photons, which are photons that kind of live only a very, very short time and have somewhat different characteristics from ordinary photons, or can. But in any case, the end result is it's possible to produce electron-positron pairs without much difficulty, actually, as soon as you're sort of pumping energy into a material. Beyond, you have to pump enough energy that it is more than the effective energy associated with the mass of an electron plus the mass of a positron. And there's this famous formula, E = mc², and that tells you sort of how much energy corresponds to the rest mass of a particle. So if you have enough energy, if you have energy equal to the mass of the electron plus the mass of the positron, that energy can cause an electron and a positron to be produced. The energy is in the form of photons, for example. Okay, so that's how you potentially can produce electron-positron pairs. You can do that by, for example, accelerating electrons, for example, with an electric field. You can just accelerate electrons and crash them into some target of some material. And inside that material, the electron, as it interacts with the atoms, can produce electron-positron pairs. And in general, you get a shower of electron-positron pairs as each of the electrons and positrons then produces more electrons and positrons until their energy goes down below the point where it corresponds to twice the mass of the electron, or mass of the electron plus mass of the positron, at which point pair production can no longer occur. But so the proton is 1,800 times heavier than the electron, so you need a lot more energy to produce proton-antiproton pairs than electron-positron pairs. But in a particle accelerator, you can get that kind of energy. A particle accelerator works by, for example, accelerating protons, it could be electrons, to high energies. And then you take those electrons and, for example, you crash them into a target made of lead or something like this, some material. And if the energies are high enough, you can get the production of a proton-antiproton pair. Okay, so that's all well and good. One of the problems is it's a very violent act, producing something like a proton-antiproton pair. Lots of energy has to go in, and these two, the proton and antiproton, come out. But typically, when they come out, they'll have quite a lot of momentum. They'll be going in some random different direction. And the main difficulty in getting sort of a bottle of antimatter is to kind of calm the antiprotons down. They're produced, and they're produced going off in, close to the speed of light in some particular direction. So you have to kind of catch them and bottle them up and make them lose energy, but lose energy without interacting to the point where they can be destroyed, where, for example, if the antiproton meets a proton, then it'll just get annihilated and turn into pure energy or photons eventually, photons and electrons and so on eventually. So you kind of have to be able to sort of chill out the antiprotons, cool down the antiprotons, without them interacting with anything. And essentially the way you do that is to use electromagnetic fields, use magnetic fields and so on, because although that is an interaction, every time the antiproton is kicked by the magnetic field, that is an interaction with a virtual photon, but those interactions do not cause the antiproton to like annihilate or anything like that. They just are something where a photon comes in, antiproton sort of changes direction, maybe another photon comes out, but it's still an antiproton there. So the big challenge tends to be to sort of get the antiprotons in a form where you can use them in a magnetic bottle or something like that. If you had something which was an actual material substance made of atoms, which have protons in them, then these antiprotons would immediately end up annihilating with those atoms. So the only thing you can do is sort of hold them electromagnetically in a place. And that was just difficult to do. So the number of kind of bottled up antiprotons that you can get is not very large. And people have studied a lot the sort of anti-atoms and things. And for example, it only was discovered, I don't know, a few decades ago now, that anti-atoms do fall under gravity just the same way that atoms fall under gravity. So in other words, it is true that the force of gravity operates in the same way on a proton as it does on an antiproton. The electrical forces, because the antiproton has the opposite charge from a proton, as a negative of the charge of the proton, electrical forces operate on opposite ways on protons and antiprotons, but gravitational forces, force of gravity, acts the same way. Not obvious that will be true, but that is what's true. And that tells one something about how gravity works relative to how electromagnetism works. The sort of the fancy statement is the particle that is responsible for electromagnetic forces, the photon, has a spin of 1 unit, and the particle, the graviton, that's associated with gravitational forces has a spin of 2 units, and that difference between the 1 and the 2 is what leads to this phenomenon that protons and antiprotons behave oppositely under electromagnetism, but behave the same way under gravity. That's just the sort of fancy versions of it. Let's see. So that's the basic answer, that it's difficult to make a bottle of antimatter just because the ways you make antimatter, and you're making it one particle at a time, but you can make quite large numbers of these particles. It's just hard to kind of cool it down and sort of collect it in a bottle. Let's see. Gosh, Carol is asking about my perspective on smart glasses with AI assistants. Is that the future of smartphones? You know, this question of how we humans interface to technology is an interesting one. I mean, we have a certain number of appendages for interacting with technology. Our fingers are a really good one, and that's a way we can put input into technology. How do we get things from technology? Well, you know, there are our eyes, and for us, our species, our eyes are the highest bandwidth way, the highest amount of information can get sort of understood by our eyes relative to other senses. So like we have 10 million nerve fibers going from our eyes to our brain. For hearing, we only have 50,000. For smell, we have even much less than that. For dogs, for example, it works differently. Their smell apparatus is noses, basically, have lots more nerve fibers relative to their ears or eyes. And so for them, you know, smell's an important thing. For humans, they're sort of, you know, there are other things like this. The total surface of the skin has lots of receptors. I think small compared to the eyes, but still quite large. And we haven't really, you know, we haven't quite got covered ourselves with little actuators where sort of every inch of skin can be used as sort of input from technology. I'm not sure that would really work very well, but so, you know, our eyes are a good source here. And then the question is, well, we're using our eyes, what are we looking at? And sort of for a while, the main thing you would look at that would interface with technology is a screen, you know, a big screen in front of you, held vertically, so to speak. Then there were smartphones, and it turned out having that portable screen, even though it's much smaller than the screen you can get sort of in front of you, is a convenient form of interaction. And the fact that you can kind of have a keyboard on the screen and so on is interesting. I mean, I have to say, it surprised me that people, you know, you can see these movies in hugely high resolution. It's really impressive. And then people actually are perfectly happy watching them on their phones. Now, phones at this point have very large number of pixels, but they're still very small, and they occupy a small field of view for us humans. Because one of the issues is when you look out into the world, there's the question of sort of what's the maximum angle that you can see on either side. I think it's 140 degrees, if I remember right, is the total sort of amount that humans can see, including their peripheral vision. If it was 180 degrees, you'd be able to see off to the side, you know, like a horse or something, which has eyes on the sides of its head, and so it's able to, you know, it can see more around itself. I mean, it's kind of like the self-driving cars that have kind of eyes on their sides as well as sort of the big eye on top, so to speak. I mean, those aren't ordinary eyes; those are LiDAR devices. Well, for depending on what kind of self-driving car it is, but this notion that you can that you have, you know, what's your field of view? Anyway, people have been happy, surprisingly happy with smartphones, which have a very small field of view. You're looking at a very small fraction of the angle that you could potentially see. So, sort of a coming attraction is all of these various virtual reality, augmented reality systems from different companies that purport to have something where you sort of put it on your head, and then it allows you to have things which are head-mounted displays, where the display moves as you turn your head. And for example, if you're looking at virtual reality, one of the big issues is as you turn your head, you can tell from the sort of accelerometers in your ears that you're turning your head. But does the scene that you see in the virtual reality display, does it move with your head? And it's been quite hard to get the scene to move sort of at immediately as you turn your head, and not to have a delay of some number of hundredths of a second or something. And that delay is, for many people like myself, something that gives one terrible motion sickness if there's a delay like that. One's brain gets very confused, and its version of telling you it's confused, its error message, is to make you feel nauseous. So that's, it's an issue with those kinds of things. But I think the thing that I'm expecting is that the sort of next generation of augmented and virtual reality displays, it depends sort of how heavy they are to fit on one's head. Eventually they'll get lighter. But I think the main thing that is probably true is that they will allow one to have very wide angle of view kinds of displays, and one is going to be able to put 10 displays in one's visual field. And that's, like I have basically 4 displays on my desk, for instance. And if I just had them virtual, sort of all attached to my head in some very high resolution virtual reality device, I could have 10 displays in my visual field. And that might be a nice thing. It might also be, as I say, that people have chosen to use smartphones that are a small fraction of their visual field. So I can't completely say that that will be something that people will really want. But I think there's then the question of how do you control all these things, and what can you use? And we have the notion of typing, we have the notion of moving a mouse. There are 3D gestures one can imagine, which have not really caught on yet. They may eventually. I kind of think that there's a certain degree of this idea of putting your fingers on keys, and the keys are in a definite place. That is in a sense, is a very streamlined way of interacting with the system. If you say, well, I'm going to, do all kinds of weird hand gestures, they're less anchored. They're less like, oh, I'm pressing the H key or something. It's like, is there a key in the air? I'm not sure whether people learn well how to do sort of precision motions that can convey lots of information in just sort of in the air, so to speak. But there are many other possibilities for how that kind of thing might work. Now, another thing, when you have a virtual reality display, there are questions about, well, what about you move your eyes? Can you pick things out by moving your eyes? Could you have a menu that shows up, and if you go move your eyes to center on that menu, it means I selected the menu, or some such other thing. So these are all things which I don't think we yet know what people are going to find convenient. I mean, the fact is that if we look at the history of user interfaces, there are all kinds of different things that have seemed important and then not seemed important. Like, oh, is it, do you hand write on your smartphone surface? That was a thing for a while. It turns out that typing is actually the thing people prefer, even though it's kind of goofy because you've got this tiny keyboard, and you certainly can't use all your 10-fingered typing there. At least young kids, I guess, might be able to, but anybody else, their hands are too big. And so you end up doing thumb typing and all these kinds of weird things, which, who knew that would turn out to be a thing that people preferred to picking up a stylus and drawing things with handwriting and having the computer recognize that handwriting. So I think it's slightly difficult to predict. Rebel is asking, was the separation of matter antimatter proposed by Feynman or earlier? No, it was much earlier. It was as soon as antimatter was known in the 1930s, people started thinking about the possibility that the universe might have a bunch of antimatter in it. I think certainly by it was widely discussed by the 1960s. And the main thing that was imagined was that matter and antimatter would be kept apart because there would be any place where they were nearby, there would be annihilation of matter and antimatter, and that would produce a bunch of radiation, a bunch of photons and other such things. And the pressure associated with that radiation would keep the matter and antimatter apart. It's a phenomenon often called Leidenfrost phenomenon, which is something where if you have a similar case, if you have a drop of water and it's on a very hot surface, the drop of water will like skid around the surface because it's kind of being suspended on a bed of steam, because right where the water drop kind of touches the very hot surface, that hot surface is boiling the water into steam right where it touches, and that steam has pressure that keeps the water away from the hot surface. So it causes that water drop to just skate around on the surface and survive much longer than it would given the heat that's coming from the surface. And the other thing to say is that the steam is kind of an insulator to heat. And so even though there may be lots of heat coming from that surface, it doesn't reach the water drop as much as it would otherwise. And so kind of a hypothesis was perhaps there will be places in the universe where matter and antimatter are held apart by radiation pressure associated with annihilation right on the boundary. And we simply don't see that kind of phenomenon in any broad way in the universe. You know, people have looked for antimatter from other parts of the universe. People have looked for that in cosmic rays coming from space, mostly from the sun, but maybe also from other sources. There even was an experiment on the International Space Station looking for anti-atoms of various kinds and didn't find a significant number. Brady is asking, are there anti-neutrons, anti-elements? Yes, there are anti-neutrons. Some particles, like photons, the anti of the photon is just a photon. But all of the quarks and so-called leptons, the electron, the muon, the neutrino, all of those things have anti versions of themselves that are different from the things themselves. In fact, for both protons, there are antiprotons, neutrons, there are antineutrons. So yes, there can be anti-atoms, and people have made anti-atoms up to quite large atomic numbers, you know, far down the periodic table. You can absolutely have I doubt an anti-uranium atom has ever been made, but in principle, you can make certainly anti-helium has been made. I'm not quite sure how far it's gone. It is not easy to do that because you have to kind of, you know, get all those antiparticles sort of cooled down to the point where they can kind of merge into a nucleus, and that's not so easy to do. Let's see. Paula asks, does technology behave differently depending on outside factors like atmospheric pressure, temperature, gravity? Is there an ideal environment? That's an amusing question. You know, when I first had an iPad, right when the iPad came out, I left it out in the sun and it got very unhappy. It has internal temperature sensors that switch it off when it gets too hot because the circuitry, silicon circuits, have just don't work if they're too hot. So most electronics, semiconductor electronics, relies on the fact that the electrons, so normally in a material, well, in individual atoms, there are electrons that are just kept sort of trapped within the atom. They just sort of connect, you know, they sort of orbit the nucleus in a sense, held in by electrical forces, and they don't escape from their atoms. In a metal, atoms are all sort of arranged together, and the sort of electrons from different atoms get shared, and there's what's called the conduction band, where electrons are kind of free to roam freely around the solid that is the metal, and that's the fact that they roam freely is what allows is what allows the conduction of electricity, because the collection of electricity is just electrons moving around, and in a metal, the electrons just move freely around. In a semiconductor, they don't move freely around, except that if you can give them enough energy, they eventually get to the state where they reach this conduction band, but there's a band gap. There's a gap of electrons below that energy aren't able to roam freely. They're just trapped within their atoms. But as soon as they have above a certain energy, they're able to roam freely in the material. And so semiconductor devices work by having putting voltages and things to effectively increase the energy of electrons, so that in certain cases, they will sort of roam freely, and in other cases, they'll be trapped in an atom, and that allows you to make switches, which can be used for transistors, et cetera, et cetera, et cetera. Okay, here's the catch. The catch is that if you heat up the material, the electrons will start running around quickly and effectively have higher energy anyway, independent of all those carefully arranged sort of voltages that lead to switches and things like that. The electrons will just be all bouncing around, and they will be moved into the conduction band. And so that means that something where you have a piece of electronics, it's all based on these semiconductor switches and transistors and all that kind of thing. You heat it up, and those will all just sort of go. None of them will work, because the electrons will all be sort of so high energy that they will reach this conduction band, and you don't get the kind of switching capabilities. And so when you make electronics too hot, it stops working. At least electronics of the kind we have right now just stops working. When things get cold, the electronics will still work. One of the issues is that if you have sort of joints between things that are made, but with soldering or something like that, where you have different metals that are next to each other, one of the things that will happen is that, well, when you heat up a metal, or any material actually, but metals as an example, when you heat them up, the atoms will, what does the temperature do? The temperature makes the atoms move around with more energy, and kind of makes them move around faster. As you heat it up, most materials expand when they're heated, because the atoms are jiggling around more and more, and so they can kind of, the atoms are all sort of held together by these forces between atoms, and as you increase the temperature, the atoms sort of get closer and closer to escaping from those sort of being held together by those interatomic forces. And so what happens is the material expands, because the atoms are all sort of getting to be on average further apart. So most materials expand when heated, contract when cooled. The issue is that different metals, depending on all of their different detailed characteristics, will expand at different rates as you increase their temperature. So as you cool it down, one of the things that can happen is they'll contract, but they'll contract at different rates. And the result of that is you get a crack between, one metal kind of contracts more than the other metal, and when they were supposed to be right next to each other, connected, that no longer works. The crack forms, and your circuit doesn't work anymore. So that's the thing that tends to limit things on the cold side. And there's kind of a normal operating temperature, I don't know, maybe minus 10 degrees centigrade to maybe a little bit less than 100 degrees centigrade, I would say 70 degrees centigrade or something like that. I'm not sure exactly how much is, you can work it out, because we know the band gap for silicon, which is what most semiconductors are made of, I think it's 1.2 electron volts. And I could do a little calculation, but I'm not sure of what temperature that sort of all goes to hell, so to speak. But anyway, so that's one feature of things, is temperature can affect electronics. Things like humidity don't immediately affect electronics, but eventually, if you get water in things, spill water on your computer, actually they behave much better on that these days, but in the past, the problem is you spill water on a computer, and lots of things that were supposed to not transmit electricity between them will start transmitting electricity. water is not a great transmitter of electricity. It's not like a wire or something made of copper, but it is a somewhat reasonable conductor of electricity. And if you have two different, let's say, copper wires that were initially on something that didn't transmit electricity at all, and you put water on those two things, the water will allow some electric current to flow from one wire to the other, which again, very bad for the circuit. I mean, we kind of know it's kind of like the, be careful with electrical devices if you're hanging out in a bathtub full of water, because, if the hairdryer falls in the water, it has, insofar as it's has electric current flowing through it, that current will flow through the water and will flow through you. And it's very bad for electric currents to flow through you. Why is it bad for electric currents to flow through you? It's because electricity is what makes muscles contract. And so if you, and this was in fact how some electrical features were discovered 300 years ago or so, 250 years ago, was if you take a muscle and you sort of put an electric current into it, the muscle will twitch. The muscle will because that's the signal that your nerve is sending to the muscle is an electrical signal, and there's a junction, neuromuscular junction between the nerve and the muscle, and it's the presence of an electrical signal that comes from your brain to the muscle that causes the muscle to contract. And so if you have an external source of electricity and it is getting into your muscles will contract. Now, the muscle, which is kind of the most important, I suppose, for all of us on an ongoing basis, is the muscle of the heart. And the really bad thing is if what's happening for the heart is the heart has there's a nerve, venal nerve, right? It's a nerve that goes through the center of one's neck, as well protected nerve that comes from one's brain that is kind of giving the heart a signal to, heartbeat, heartbeat, heartbeat. And the heart then responds. The way a heart actually responds, it really only needs to be given a little kick. And then the structure of the heart itself causes it to have this quite complicated contraction motion and so on. But the problem is, if you get if you get an electric current that gets into your heart, so to speak, it will make the heart and the muscle of your heart contract in a way that isn't the right way for it to contract, because it's carefully set up to contract just based on these particular nerves, based on an electrical signal from these particular nerves. And so that is really bad because it will cause your heart to fibrillate, which means it's kind of just wobbling around and responding to electrical signals as a muscle, so to speak, but it's not doing that in a nice organized way where it's pumping blood through you. And if it continues to fibrillate and just sort of wobble around, then blood won't get pumped around your body, and that's bad news. And that's why, for example, a defibrillator is something where you're putting actual electrical signals through the heart in such a way as to get it to kind of wake up and stop wobbling around randomly and start beating in its organized way again. But if you get a electric shock that passes current across your heart, it can be a bad thing because it can stop that fibrillation process, just as a defibrillator can stop that fibrillation process. And so the rule of thumb for people is, if you're going to touch something which is kind of a electrical outlet or something, stick one hand in your pocket, so you only have one hand that is that's might get an electric shock, and then the muscles in that hand will contract to maybe that arm, and that's bad. But it doesn't. If you have your two hands and they're on different, you can get an electric current from one hand to the other. That kind of goes through your heart, and that's really bad news. So it's kind of like, you keep one hand in your pocket when messing with electrical stuff principle is that's why that's worthwhile. But okay, that's but back to how electronics works. Electronics does not care about gravity, at least not any kind of gravity that we typically encounter. Now, electronics, I suppose the one case is if you have something in in something which is being rammed into something at very high speed, and it has a very high deceleration. Deceleration is kind of acts like gravity. You can't actually distinguish between, if you're not seeing the outside world, you can't distinguish between pure acceleration and the result of the force of gravity. That's the so-called principle of equivalence. But in any case, sort of gravity of a kind that we find on the Earth or something doesn't affect electronics in any significant way. Gravity does affect, or acceleration can certainly affect things, because if you decelerate fast enough, it's mostly mechanical problems that occur. It's mostly sort of wires will come detached and things will get sort of physically damaged. It's not that the electronics will have, it's not anything sort of internal to the electronics. Now, I mean, there are other things that happen. So, for example, cosmic rays, high energy particles coming from the sun, mostly protons, that hit the upper atmosphere of the Earth, and most of those things are stopped by the atmosphere of the Earth. Not much gets through at sea level. It's mostly muons at sea level, particles that they sort of survive a bit further in the atmosphere. But if you go to a place that's, at a high altitude, like, Denver or something like that, that's roughly a mile high, then there's less volume of atmosphere above you. And so the cosmic ray protons that hit the upper atmosphere of the Earth, many more of them survive to where you are in Denver, let's say, than at sea level. And so that has the effect that when one of those protons goes through a piece of electronics, it leaves a trail of ionization. It leaves the energy associated with that high energy proton, for example, will rip electrons out of the atoms that they're in. And that will lead to effects that will sort of change the electronics of what happens in a piece of electronics, a microprocessor or something like that. And so if you have a memory chip, you will routinely get errors in the memory chip associated with cosmic rays. And in fact, that's even used years ago. This is late 1970s. I suggested to people, gosh, why, given that fact that the cosmic rays lead to errors in memory chips, why don't you just use that to detect particles? And I think people have independently figured out you might be able to do this, but at the time, people say, "Oh, no, you wouldn't be possible." Now, semiconductor particle detectors are very, very, very common. It's a very common way to try and detect particles. But in any case, the thing that so electronics, memory chips, things like that, when there are these particles coming from cosmic rays, they will change the data that's in that's in these in these bits, and and so that's a sort of a different effect. So back in the day, this is early 1980s, when computers, sort of very high performance computers, were delivered to places that were at high altitude, particularly Los Alamos National Lab, big physics, etc. research organization, happens to be at 7,000 feet altitude in New Mexico. And when computers would be delivered there, they would regularly behave somewhat differently than they did at sea level as a result of cosmic rays. Although what really saved that is a typical memory chip nowadays, and semiconductor memories that existed at that time as well, have error correction. So in a let's say there's a 32 bits of memory, actually what's really there is like 34 or 35 bits, and those extra bits are used to check the other bits and correct any kind of error that might arise from cosmic rays. So that's kind of a thing for that. Now, when you try and use electronics in space, it's a big mess, it's complicated because you have lots of cosmic rays, and it's non-trivial to get the electronics to kind of survive that. You have to kind of harden it, and it's not even clear in general how to do that. If you have multiple copies of the CPU or something, you can have them kind of, at least they won't all be zapped at the same time, probably. And you put kind of shielding to prevent the cosmic rays getting to your piece of electronics, things like this. And also the electronics itself can be made so that it doesn't depend quite, it requires more of a kick to flip a bit from a 1 to a 0 and so on. Let's see. Yes, Atom comments that deionized distilled water won't conduct, or at least a lot less than ordinary water. This is true. Evangelos is asking, how about solar flares? How do they affect technology? Yeah, well, they put lots of particles, actually, particularly electrons, I think, into streaming towards the Earth from the sun. They have pretty bad effects on lots of electronics, particularly satellites, not shielded by the Earth's atmosphere, but even on the Earth. I think we talked about this in another one of these sessions. The effect on the power grid, on electric power lines, things like this, can be fairly dramatic. I mean, the last really big such thing, so-called Carrington event, happened in 1859, when there were already telegraph lines and things like this, but not the same kind of dependence on electrical systems as we have today. And it's an interesting question. Let's say, what would happen in the event of a really big solar flare to all the electronics that we have? One of the pieces of good news is that the electrons from the sun go a lot slower than photons from the sun. And so we'd have a day or two of warning, probably, that the big pile of electrons are coming our way. I think maybe is it a day, or is it only a few hours? I'm not sure. But there are satellites, there's at least one satellite that watches the sun for these kinds of things. I'm not completely sure what the, I don't know quite what happens in what's been figured out about what the warning system looks like. I mean, it's kind of one of those, everybody's phone is going to buzz and say a big solar flare is coming. And it's like, so what are you supposed to do about it? I think you switch off electrical systems and kind of hope for the best, and hope that the amount of induced current in these electrical wires is not large enough to independently cause trouble. Let's see, I3 is commenting on a gamma ray burst. I was not paying enough attention to know about saying that it's the biggest of all time burst. I was not paying enough attention to know about that. I mean, gamma ray bursts are a phenomenon seen in distant galaxies, and I mean, there are a variety of theories, but I think some of the theories have to do with kind of matter being dumped into black holes and things, and as before the matter is kind of swallowed up by the black hole, the gravity of the black hole makes it swirl around very fast, because things that are in orbit around the Earth, to maintain an orbit around the Earth, you go in low Earth orbit at about 17,000 miles an hour. To maintain an orbit around the sun, it's different speeds, but less than 100,000 miles an hour for sure. To maintain an orbit around a black hole, you have to be pretty much going at the speed of light. And so what happens is that material that's swirling in towards a black hole, it will kind of swirl around, and it will be made to go extremely fast. And when that happens, it's kind of continually being accelerated as it's held in this orbit. And one of the features of accelerated charged particles is that they radiate electromagnetic radiation. And in particular, in that case, when it sort of quickly swirls in, it radiates intense electromagnetic radiation, and we perhaps see that as a gamma ray burst. I don't know the details of that one. All right, we should probably wrap up soon here. There's a question here about what determines the color of a leaf when the weather changes. And I should know the answer to that. I think I did once, and I don't really know. I mean, basically, these are leaves that are dying, and the chlorophyll that makes them green is somehow breaking down, but I don't know exactly how that works, and ending up with different colors. I mean, the fact that chlorophyll is green is not unrelated to the fact that it is absorbing photons from the sun, and it is since green is the place where there's sort of the most photons that come from the sun. That's where the leaves are green, because evolution has set things up so that the one's preferentially absorbing. Is this right? Is this right? Let me think about this for a second. One wants to absorb, so that the green light is obviously reflected from the leaf. So am I confused here? Red algae, which live under the ocean, have, the ocean is absorbing light. Am I getting myself confused? I think it's the case that the red algae are red because they only the red light survives at that depth in the ocean. And let me think about this for a second. Well, in any case, the green color is associated with what what will allow the most relevant light from the sun to be absorbed. Let's see. Oh boy, here's a question from Gist. Could there be nanites waiting for more favorable conditions to multiply? Nano-sized sort of living organisms in samples we bring back from an asteroid. How can we be sure there aren't any? That's a good question. That's a good question. I mean, I think that's kind of like asking the question, given, to know for sure, it's like, given this microprocessor, does it have some sort of malicious circuit that's been burnt into the microprocessor? Can we tell if the thing is going to do something bad? Can we tell if this particular viral sequence that we could build into a virus is going to do something bad in humans? I think it will be pretty hard to tell if there's particularly if let's say there was an alien life form or something that was on a very tiny scale, but was as soon as it was given, water or something, it suddenly can start to replicate, and it has some complicated chemistry or something that causes it to do a perhaps more efficient form of the replication that biological cells do. And could that sort of destroy the Earth or some other bad thing like that? I think I think to be absolutely sure, it's not easy. I think it's hard to know things that one doesn't know, things where one could there be a mechanism that would cause the asteroid rock to suddenly start replicating and doing crazy things? In principle, they could be. Is it likely? No, it's not likely. But one doesn't know for sure. It kind of reminds one of the fact that when the first astronauts came back from the moon, they were quarantined for 10 days or so because people didn't know whether there might be moon viruses that they might have picked up. And now that seems kind of absurd, but it's not self-evidently obvious. And I think the possibility of some sort of lifelike replicating thing that is triggered by kind of interaction with something different than it's usually interacted with is an amusing concept. I think not very likely. I mean, it reminds me of the movie 2001: A Space Odyssey, which features a big slab that's been buried on the moon for some large number of years, which has the feature that as soon as it sees sunlight, it sends out some intense radio signal, which starts a whole giant plot arc in the movie. But that was kind of the concept that, the aliens buried it there and trying to wait until somebody would notice it had some weird magnetic feature. By the way, there are magnetic anomalies on both the Earth and the moon, just like in that movie, but not known at the time the movie was made. But in any case, where you kind of find it because it has this weird magnetic feature, and then once it's excavated, then the aliens know some clever folk were around on the Earth and the moon because once it's excavated, it can see the sun and do different things. So it kind of wakes up when it sees the sun. And so I suppose the concept here would be the nanites wake up when they're brought to Earth and start eating us, which would be a bad outcome, I think. All right, we should probably wrap up there. So thank you for some interesting questions. I see a whole bunch that I didn't have a chance to get to, and I'll look forward to doing this again another time. So thanks very much, and bye for now.